So maybe let me start by recapitulating what we have done yesterday. So we started studying thermodynamics in expanding universe, and we said that there's this sort of exact description through the Boltzmann equation. But Boltzmann equation, it depends what you put on the right-hand side. You can put all the data physics on the right-hand side, and so you can hide there anything. But anyway, solving Boltzmann equation is quite complicated, even in the simplest approximation if you make the right-hand side to look very nice. So that's why we actually be doing mostly the equilibrium thermodynamics. And so you establish, despite the fact that the universe is expanding, you can sort of establish a local thermodynamic equilibrium, provided that the collision time between the particles for some special reaction is actually much smaller than the Hubble time in which the universe significantly expands. Or in other words, that the reaction rate of my collisions or of my reactions is much bigger than the Hubble parameter. That's the same thing. Okay, so under this assumption, you actually maximize entropy, and then you have more or less standard statistical physics. So your distribution function is given by this distribution where plus minus 1 stands for fermions or bosons. And so once I know the distribution function, I can calculate the particle density, the energy density, or the pressure by those formulas I gave you yesterday. Okay, so now there are two important limits where you can calculate these things. So the relativistic limit, so basically you say that the only thing which has units of energy is the temperature. Everything else is approximately zero. So I just neglect the mass of the particles or the chemical potentials. And then just based on dimensional analysis, because this is the only thing which has the units of energy, then the particle density is 1 over volume. So, and it goes like the energy to power 3, so it's T cubed. The energy density is, there's one more energy there, so T to the 4, and the pressure is T to the 4 as well. So now if you actually calculate, so I calculated this guy here for you. You will calculate in your homework rho, and you will calculate P. But if you do that, then you may study what is P over rho, which is our W, and you'll find that it's actually 1 over 3. That's precisely what we are using before, is that this is our equation of state for relativistic particles. Right? And this is true. So of course, what stands here depends on whether you are boson or fermion, but this relation is universal for both bosons and fermions. So the other limit is the non-relativistic limit. And again, you will study it more in your homework, and that means that basically the temperature is now negligible. It's much smaller than your rest mass of the particle. And then we found that the number density is suppressed by this mass, which we said, well, thermodynamics hates massive particles, so it tries to basically exponentially decay them, exponentially kill them. So in other words, if you have some massive particles, let's say proton and antiproton, what you want to do is that you want to change them to something which is relativistic and more energetically favorable if you want. So you rather annihilate proton and antiproton and form photons which are relativistic and happy. Right? So what this is basically encoded in this exponential decay. So similarly, you would find, again, your homework is that the energy density is something like m times n, and the pressure is T times n. So now if you, again, study W, which is P over rho, then P over rho is just T over M in this approximation, but of course that is 0 in our approximation because T is much smaller than. So this is what we are saying, that if you are non-relativistic matter, you basically have 0 pressure when compared to the energy density, and that's your equation of state. So W equals to approximately 0. Okay. So this is what we have in equilibrium. Now, what is actually very nice about the universe is that it behaves, well, if you want to study thermal history of the universe, you better use some conserved quantities. And in our case, it will be the entropy which is conserved. Okay, so Turing thermal evolution of the universe the total entropy is approximately conserved. So this is relatively simple to establish in equilibrium. So if you have thermal equilibrium, then you can show by three-line calculation that this is true. Well, if you think about first law, d equals to TdS, well, usually ds doesn't change, right? Unless I do something crazy. So if I undergo slow expansion or whatever, then ds doesn't change. So in equilibrium, this is sort of okay. You have to do wild processes so that this is not true. So out of equilibrium, this is not obvious, but we can use the fact that basically all entropy in the universe is stored in the photon bath. Okay, so it's really the photons which carry most of the entropy, or the relativistic particles, if you want, which carry. So as total approximately equals to relativistic bath, which is mostly photons. Okay, so I told you yesterday that there is this, when the baryons were created, you always created one more proton than antiproton, and that happens in 10 to the 9. It's 1 to 10 to the 9. So in the end, you have 10 to the 9 times more, 10 to the 9 times more photons than baryons. So that means that the entropy of baryons doesn't really contribute, right? So now, is this true what I'm telling you? Is it really the total entropy of the universe mostly stored in photon baths? What do you think? Is there some other significant contribution? Well, neutrinos, yes. Something more exotic, maybe. Yeah, maybe. So, okay. So definitely black holes. So black holes actually store so much entropy that it's many times more than actually the photons do. So in the end, the total entropy of the universe will be dominated by black holes. But of course, black holes sort of decoupled from everything what we are saying here, right? So they don't really participate about whatever we are going to discuss here. So that's why we can forget about that entropy. So anyway, so as total for our case will be actually given by a photon bath. And so if you have any non-equilibrium process, there will actually be some entropy production in that non-equilibrium process. But when you compare this to S total, it's completely negligible. Okay, so this is our entropy production, but we can completely ignore it if we just talk about total entropy of this photon bath. So that means that basically our expansion of the universe is adiabatic. If you don't like my explanation, find your own explanation. but basically it's true. Okay. So what it means is that if you take the total entropy, it's an extensive quantity, so you can put it as an intensive S times the volume, and so this thing is constant. Or equivalently, if I want to talk about a small s, which usually people do, because the volume goes like a cube, then s must go like a minus cube. Okay, so s is proportional to 1 over a cube, small s. And so people use this in cosmology all the time, that the intensive part of the entropy actually behaves like 1 over a cube. Okay? So now, let's have some fun. Or maybe before we have fun, let's establish what actually S is in our equilibrium thermodynamic description. And so for that, we will consider relativistic particles. So relativistic, well, consider a bus. Let's have a bus of relativistic particles with species. And so because they are relativistic, we neglect all chemical potentials and so on. Neglect all mu's. That means that your energy density will be only function of temperature, and the pressure will be function of temperature, and so on. But also, your intensive entropy, or the entropy density, will be function of temperature only. Okay, so now consider this situation. Then you will show in your homework by 3-line calculation that dP over dt at constant s, that's what we have, is rho plus p over t. And that's your homework 1. Maybe you have done that already. Okay, so what is really key is that you can neglect the chemical potentials, and then you are in the relativistic approximation. Okay, so that's first result. Second result is that we have these interesting relations between various thermodynamic quantities, which are called Maxwell's relations, right? And so one such relation which is useful for us is this one here at constant t. It's a Maxwell relation, one of them. So now, of course, if I take S to be small s times V, where small s depends only on temperature, then this is just small s. The right-hand side, right? I just plug here that big S is S times V, differentiate V, and I get small s. Okay, so based on these two relations, so this is the left-hand side, this is the left-hand side, we conclude that small s is just rho plus p over t. Okay? So that's how we calculate the entropy density in our universe. But of course, we already know what rho and p are because we calculated them previously. Right? We have the formulas in our approximation. Rho goes as t to the 4, and p goes as t to the 4. So s goes like t to the cube. But if you calculate those coefficients exactly, you have exactly what small s is, right? So in particular, and that's again, you can check this with respect to your homework. So for bosons, this gives you 2 pi squared over 45 t cubed. And for fermions, it's just 7 over 8 for the bosons if they have the same temperature and degrees of freedom. Okay, so this is for 1 degree of freedom. So now, typically you don't have just one fermion in your bus, or one boson in your bus, but you have many of them. And sometimes they can even be sort of decoupled one from another. So that means they can have different temperatures. For example, the photon bus has a different temperature than the neutrino bus at this point. Right? So you can have a bus of total things, but they can be at different temperatures. So let me say that So let T be the temperature of the photon bath, or always, so temperature of photons. And T. Very good. It was very okay. And then Ti be the temperature of the species I. So temperature of species I. And they don't have to be necessarily the same. Okay. So, and the statement is that if you want to calculate the entropy density of this bath, which contains all these various species and so on, then it's just something so that it works, which is called G star of S, and whatever you have for 1 degree of freedom, 2 pi squared over 45 T cube. And so this number has to take into account that you have various species and they can be at various temperatures and so on. So this number is just G star of S is sum over bosons Ti over T cube and plus 7 over 8 sum over fermions Ti over T cube. Similarly, for the energy density, okay, again, I'm giving you the result for your homework, but that's okay. Pi squared over 30 T to the 4. So again, this number makes sure that it works for the mass of the particles. But now you know that these things go as T to the 4. So it will be again sum over the bosons Gi over T to the 4 plus 7 over 8. I hope this is correct. The same factor. Fermions Gi Ti over T to the 4. Okay, so in these formulas, okay, so we know temperatures what they are. So now what are small g's? So small g's are basically the internal degrees of freedom of your given particle species. Okay, so Gi are internal degrees of freedom. For example, the spin states. So if you have a photon, then you simply have degree of freedom is 2 because you can have 2 polarizations of the photon. Okay, and so that's how you calculate this G star of S and G star. So these are called effective numbers of either for the entropy or for the energy density. You calculate them in this way, and notice that if you have something which is really decoupled there. So if some Ti is not equal to T, then of course this guy is different from that guy, right? Because it's a different prescription. If all the temperatures are, all the species are at the same temperature, then they are the same. Okay. But anyway, so you'll play with this. To estimate these guys at a given temperature, well, you'll play with it in your tutorial next week. But basically, what you have to do is that you have to think about which of the species at that temperature are still relativistic, right? So how many relativistic species contribute to my bath, right? And that's given by, well, if you have, I don't know, 1 MeV and probably protons, the temperature is 1 MeV, then protons probably are not relativistic, right? So they will not contribute to this guy, but some of the particles may be. So electrons actually are relativistic and will contribute. Okay. So this is basically the number so that it works and it nicely gives you the right result you want. Okay. So now let's have fun. So this is just a tool, but let me mention some very interesting phenomenon which may happen in the expanding universe, and that's called decoupling. Coupling and freeze out. And so far what we discussed was just the equilibrium description. But actually the most interesting things happen when you are out of equilibrium. Because, well, okay. So as T drops, it may happen that the reaction rate decreases and no longer satisfies that equilibrium condition which we have there, so that gamma is much bigger than h, right? So for here, so for gamma which is approximately equal to h or smaller than that, you say that the species I, well, gamma I, then the species I decouples from the rest. Decouples from the reaction. And it's no longer in equilibrium, couples, and no longer in equilibrium is the rest of the path. Okay? And so this leads to the freeze out of the particle. So leads to freeze out. I'll draw a picture for an example. So freeze out. Yes?
I understand the idea that if the temperature drops, you have, well, particles have less energy and they interact less. But at the same time, if they're too energetic, then also they might, if they have a very strong, very high temperature, just like go through each other, they couldn't really interact. Like, when
is
you
that
have,
true? Well, I was saying that the cross section decreases.
Yeah.
Well, they still bump into each other, but maybe they, it's just a little bit also.
For example, if you have like a proton and an electron, and they had too much energy, they wouldn't get to a bound state.
But, okay.
So,
but the higher the energy is, more frequent are interactions. So maybe even if each interaction is, less effective, then it's not many more. Yeah. Well, okay. I'm just giving you a typical example of what happens here. But yeah. Okay. So freeze out of massive particles. And so what freeze out means is that their abundance does not follow the thermal equilibrium equations as we derived over there, but rather actually their number remains constant. Okay, so abundance remains constant. Approximately constant. So which means that the particle number is sort of preserved. If that is true, then the particle density, well, it's a number of particles divided by volume, so it goes like 1 over a cube, right? So then it decreases like 1 over a cube after the freeze out. Okay, so let me give you a very interesting physical example of what people think could have happened with dark matter. Okay, so example, and this is not only for illustration, but some people really think that this is the key for understanding cold dark. So cold dark matter. Let's say that cold dark matter is described by a particle chi. Okay, so now below m chi, so particles are relativistic if they have energies at the temperature which is much bigger than m chi, the rest mass. If they're approximately m chi, well, they start to be non-relativistic. Okay, so particles, so below m chi, particles, and let's say that I have chi, but I have chi bar, chi and chi no longer relativistic, and if you look at your what equilibrium thermodynamics gives you, they are exponentially suppressed, right? So that's n is proportional to e to minus m over t. So they should be exponentially suppressed. They become exponentially rare. Okay, so now let me make another assumption that suppose that the only way to destroy particle chi is when it meets its antipartner and annihilates to produce gamma. So that the only way to destroy chi is through annihilation, is through chi plus chi bar into 2 gamma. Okay. So now that's the assumption. So now as the reaction rate of this, so this is some, reaction rate gamma. So as the reaction rate gamma is now smaller than h, let's say, then this reaction no longer goes on. So for example, you may think about it, well, I have this particle chi and it's happy to meet its antipartner and annihilate to gamma, but at some point this particle chi is very, very lonely because its abundance is exponentially suppressed, right? So it takes really, really long time to find a partner, or at some point it will never find its antipartner to annihilate with. Okay, so if that is true, then of course this annihilation doesn't occur anymore. I cannot find my antipartner to annihilate with, so my particle number is conserved. Okay, so let me draw a picture how the abundance of these things might look like. So, okay, so here will be the particle number m chi divided by t cube, and here will be my m chi over t. So basically, how below the temperature m chi I am. So now if this guy is 1, this guy is 1, so I'm relativistic all the way up to here. So if you are relativistic, you know that your particle density goes like t cube. So this thing goes like constant. Okay, so this is my evolution of the particle. It behaves like a constant because I'm relativistic. That's my particle density. So now as I start to be non-relativistic, then looking at your non-relativistic formula, I'm exponentially suppressed, right? So I should go in principle like crazy down here. Right? But it may happen that at certain point, let's say, I don't know, 10, over here, I have the freeze out. So let's say that gamma approximately equals to h around that point here. So that means that below that, I simply cannot find my antipartner to annihilate this. So instead of following this exponential decay, I rather go this way here. Okay, so that's the freeze out. M chi over t. And so after that, my particle number is conserved, and again, my density goes like t cube, and that's why this is basically a constant in this graph again. So if you look at this picture, so we are very, very lucky to have freeze out. Because if we didn't, and so we simply follow the equilibrium process all the time, there wouldn't be any particle chi left. It would just be exponentially suppressed and it wouldn't exist anymore. But because the freeze out happens, I can still observe some particles chi, right? So that's the whole picture, and that's what people think. Some people think that might have happened. It's like a prototype, a framework. What could have happened with this dark matter, this freeze out? Okay. Questions? So it's really the departure from equilibrium which gives you that we see something interesting. So let me just make a few notes about the chemical potential. So if you want to study these things, well, more exactly, and you will, then you need to know how the chemical potentials behave. I'll just give you a few prescriptions how to deal with them, and if you are interested in more to study these things, you can read Mukhanov's book, where this is discussed in, I don't know, 30 pages or so. So I'll just give you some chemical potentials. And I'll just give you really a few examples how in simple situations, how to deal with that. So because you have QFT, then particles can be created and annihilated. Because can be created or annihilated. So now, unless there is some conservation law, then the chemical potential is equal to 0. So unless conservation that would, preserve the number of particles, protecting particle number, then the corresponding potential is equal to 0. So an example of this? Very good. So for example, photons. So you know that you can create or annihilate photons and it doesn't cost you anything, basically. So if you think about, you can understand this from the first law. So you have D equals to TdS plus mu dN. So D equals to TdS plus mu dN. So that's the, how many. So now, if it doesn't cost any energy to create or annihilate the particles, right? So let's forget about that term. But T equals to mu dN. So if this guy is 0, I can change the particles, the particle numbers. Then mu must be 0, right? That's the only possibility. Okay. So mu equals to 0 for photons. So now we have equilibrium process like AB reactants go to CD reactants, and the process goes both ways, and it's in equilibrium, in chemical equilibrium. Then mu A plus mu B equals to mu C plus mu D. If it's not, if left-hand side is bigger than the reaction, or smaller, then the reaction goes one way or the other. This is preferred one or the other way. So for example, if I have electron plus positron to gamma, then mu of gamma is 0. So I immediately conclude that mu of electron is minus mu of positron. Okay, so mu of electron is minus mu of positron. Okay, so that's the second simple cookbook rule. So now the truth is that mu in general, they depend on temperature. On temperature. And so because the temperature in our universe is changing, then of course mu evolve in time. Do you have a question? No? So how to find this evolution in time or evolution in temperature? So let me just do a very, very simple example where, well, okay, so first the general statement. So number of conservation laws gives you the number of independent chemical potentials. So let's say that I have a conservation of the lepton number. So lepton number. So delta Ni plus delta N mu I over S. So how many? Okay, so I is electron muon or tau. So if I change that many electrons and that many corresponding neutrinos, divide by the entropy density. So I'm saying this is constant. Okay. So now it's the last problem in your homework, which I don't expect you to do, but so that's why there is star. So if there is star, you don't have to do it. Okay. So, but anyway, you would show there that for relativistic fermions, this, how their number changes is given by, so not how their number changes. What is the difference between fermions and antifermions? Sorry. It's proportional to T cubed mu over T. So this is your homework to show. So again, so the number must be proportional to T cubed. So, but now I'm taking into account the chemical potential. If I didn't, there wouldn't be any, I wouldn't, well, okay. So it still has the energy cube units, but now the chemical potential is like a first order expansion in mu over T here. So this is that. So now if you plug it here, then you will have mu over T and mu over T, and then you have T cube and T cube, but S goes like T cube as well, right? So from here, you can read that, for example, for electrons, mu of electrons plus mu of neutrinos corresponding to E divided by T, which comes from here, is approximately a constant. So it gives you how the chemical potential, evolves as the temperature changes. Okay. And as I said, so these are just a few examples how you deal with chemical potentials if you want to do more accurate calculations. If you're interested more, see Mukhanov. Okay. For details and more. So if you really want to do your essay on these things, you need to study chemical potentials more. Yeah. Questions? No? So that's thermodynamics in expanding universe. So again, so basically all the time you have like equilibrium processes, but it's actually the departure from equilibrium which gives you something non-trivial, which gives you that you have a freeze out, that you have something that survives this exponential decay and so on. And if you wanted to calculate really, let me show this picture one more. So if you look at this picture again, so the equilibrium thermodynamics works very well here, all the way basically up to here. So you can calculate the freeze out time that when gamma equals to approximately equals to h gives you usually the right time when the freeze out is using equilibrium thermodynamics. However, then equilibrium thermodynamics gives you this. So in order to get this departure from equilibrium, you need to use the Boltzmann theory actually. or you need to say, well, use some other approximation. But equilibrium approximation is no longer good to describe that result. Okay. So now the most interesting phenomenon, and that's the Big Bang nucleosynthesis. So let's use what we have learned about these thermodynamic things, and let's apply it to this very, very important phenomenon. So today I'll just give you a background, and we will continue the calculation on Monday. But basically the whole thing is about our periodic table. So if you plot a periodic table, it looks approximately something like this. Okay. So that's our periodic table. And then we have the helium, the hydrogen here, and then we have the helium here, and then I don't remember, but there is an iron here. Okay, so that's our elements, which we know, and then you may measure how many elements of these are in average in our universe. And the truth is that basically it's if you forget everything else and you just remember hydrogen and helium, that's enough. Okay, so by mass, universe at large. So again, if you take the whole universe and then it's 75% of hydrogen. And it's 25% of helium. And everything else is just tiny little seasoning, right? So this is all there is, basically. Okay, so that's the observation. So now the question is, where, for example, the helium and other elements were produced, right? So how they were produced and when they were produced and so on. So okay, so the question is when were all these beautiful elements which we have were produced? When were produced? And so this is a beautiful piece of 20th century physics, basically half of the century. And so mid 20th century people thought about these things, and this century. And big names like, I don't know, Bethe, Fermi, Fowler, Gamow, Hoyle, all these people, like all these great physicists actually sort of, could answer this question. Okay, so it's it's real physics. It's not like string theory today, right? It's real physics where you actually explain something. Okay. So what they noticed is that if you look at various elements, then up to the iron, the elements are thermodynamically stable. So Fe, the iron, is the most thermodynamically stable element. So now up to iron, so all these things up to here, you can cook them in stars. So up to this, we can cook these things in centers of massive stars. And so we can make them like thermodynamic making. Basically, making, which is fusion, right? So if you fuse lighter elements into a heavier one, you gain energy. And so that's thermodynamically favorable. So up to iron, this is true. So yeah. Okay. So now heavier elements, it wouldn't be thermodynamically favorable to cook these heavier elements, but so heavier elements are produced in shocks. So for example, if you have supernova explosion or whatever. Okay. So this theory, about the massive stars and so on, was also developed by the same people at the time. So and then the question is, does this theory really describe what we see, 75% of hydrogen and 25% of helium? Okay, and so there was a debate, but you can basically very quickly conclude that it cannot be so. So this theory cannot explain abundance of lighter elements. Right? So for example, like, helium, lithium, and so on. So what I will try to show you in a three-line calculation is that simply you cannot cook 25% to be in helium. Okay. Okay. So let me show you this three-line calculation. So take, for example, the helium. So we have 4 helium. And so that guy has binding energy 28 MeV. So binding energy 28 MeV, which means if you destroy it, well, if you fuse it, you get 28 MeV out of that. So fusion gives you releases. Now you have, okay, so helium consists of 2 protons and 2 neutrons, so 4. So releases, so 28 divided by 4 is 7. So 7 MeV, which is something like 10 to the minus 5. I don't know what erg is, don't ask me. Per baryon. Okay, so per each baryon, I release that 7 MeV energy when I fuse helium. So now, if 25% of baryons are in helium, so if 1 over 4 baryons fused into helium, and so let's say in the whole time of the universe which we have available, so during 10 to the 10 years, which is, well, basically the history of the universe, which is, by the way, 3 times t to the 17 seconds, then you can calculate, how bright the sky would be. So this is described by a luminosity to mass ratio. So so if you see how much mass is there and how much luminosity you get from that mass. So the luminosity mass ratio well, L over m baryon. So now I am just, every force is fused. Now I get 10 to the minus 5 erg per baryon, which has the mass of the proton, and this happened in 3 times 10 to the 17 seconds. Okay, so the luminosity is the energy per time, and I'm dividing by the corresponding mass. And if you calculate this, it gives you something like 2.5 luminosity of the sun divided by mass of the sun. Okay, so this is the luminosity which you would get. So now, is this brighter or darker than what we see? What do you think? Huh?
Very bright.
This is quite brighter. Very good. So, you know, what is observed is L over M. Baryon is small or equal to 0.05. I'll start over M sun. Okay. So if you compare 2.5 and 0.05, you will immediately see that at most 0.5% of helium was actually fused in stars. Okay, so otherwise, if all the helium were fused in stars, then our sky would be just very, very bright, right? Because we would just be seeing all that energy which was there. Okay. So this one-line calculation shows you that really it must be a different theory. It cannot be that you form all these elements in massive stars, but there must be another theory. So this theory is that you say, well, our universe was so hot that I could actually fuse my helium at the beginning by basically Big Bang, if you want. So this is back in favor. So let me now show that first moments after the Big Bang are the right thing to do after Big Bang. And this was basically a big support for the Big Bang theory, that you had your universe very, very hot, and then where you could fuse these things. So fused here. Okay. I have 2 minutes. Very good. And then Dennis will not like me. Okay. So now what we will do on Monday is something which is called back of the envelope calculation. So basically the aim is to get the right result, well, to some 100% reliability, just in doing very, very simple calculation. And so person who was very famous for this calculation was, for example, Gamow. So he could really, take a scrap of paper and or Fermi. Fermi was also very famous. Okay. So now just a few estimates. So, at temperatures which are quite big, around 100 GeV, well, usual particles, all relativistic. By usual particles, I mean protons, neutrons, electrons, and so on. Okay, so that means, again, that there n is proportional to t cubed. Okay, so that's one thing which we realize. Another thing we realize is that if our temperature drops to, let's say, 1 GeV, then the protons are no longer, well, that's the time when the protons are non-relativistic, right? So, and thermodynamics eats protons, protons and neutrons, and turns them to photons, right? I remind you this very important ratio eta, which I mentioned yesterday, is that's the 10 to the 9. So number of baryons divided by number of photons is 10 to the minus 9. Okay, so this ratio is very, very important for basically how many helium you formed and how many deuterium you formed and so on. And I'll try to explain it on Monday a little bit. But it's really this ratio which governs a lot of things. And if you start playing with this ratio, you get different results. Okay. Okay. And then, so this is, okay. So protons and neutrons disappear. But still, most of them disappear and they start exponentially decaying, right? Protons, neutron goes to gamma, and then they suffer from exponential decay due to the thermodynamics. Okay, but they are still sort of kept in equilibrium due to weak interactions. So weak interactions can change protons to neutrons, can do various things. So at few MeV, what happens is that these weak interactions are they are not strong enough. So weak interactions become inefficient. Okay, and so this will have two consequences. So first of all, neutrinos, which couple to matter through these interactions, they decouple from the plasma. So that has two consequences. So neutrinos thermally decouple from plasma. Okay, so that's why they have different temperature, and you will study that. Well, we studied it a little bit on Monday, but then you will study it in your tutorial. And then second is that there is no more chemical equilibrium between protons and neutrons. So chemical equilibrium between protons and neutrons sort of breaks down. No longer persists. So up to now, up to these few MeV, you have really, the protons can absorb some neutrinos, protons can absorb some electrons and form a neutron, or the other way around. And then the important thing which allows that is the neutrinos. But once the neutrinos sort of decouple from the rest of the matter, then this reaction doesn't hold. So at that point, protons are on their own, neutrons are on their own. Protons are very stable, so they are here forever. But neutrons start to decay. And they start to decay very, very quickly. So if we wait more than 3 minutes, there are no neutrons left, and we don't have any heavy elements, right? So you have to really, within these 3 minutes, you have to act, and you have to capture these neutrons into the nuclei so that you can have heavy elements. And let's discuss this on Monday. Thank you.